Hey everyone, welcome back. So in this series of A2 chemistry revision videos, we're going to be talking about electrochemistry today. So in electrochemistry, the first kind of topic that your syllabus wants you to know is the idea that Faraday's constant is actually equal to the Avogadro's constant times the electronic charge. This equation can be used to prove the value for Avogadro's constant, which is something we do numerically. What happens is, they give us the data, for example, some electrolysis, and they tell you how much mass is deposited on cathode or the mass of some kind of gas being collected in electrolysis. And they expect you to do some calculations to find out what is the Avogadro's constant. Building upon that, I have written these steps for this Avogadro's constant, but I obviously figure out that we can't understand the entire calculation by just reading the steps. My recommendation is that watch the video where I have solved one of those constant value calculations, and then you can figure out how we do it. Another few things we need to understand from this chapter is the idea that what standard electrode potential, so it's the potential difference produced when a half cell is connected with a standard hydrogen electrode at 298 Kelvin and 101 kilopascal. Now 298 Kelvin and 101 kilopascal are standard conditions and there is no escaping them. What's standard cell potential? So it's the whole cell potential is the potential difference between two half cells. At the standard conditions, I would never recommend you writing standard conditions. I would always recommend writing the whole values for them. And you have to also mention that all the electrolytes have a concentration of 1.00 mole per dm cube. What's standard hydrogen electrode? So standard hydrogen electrode has some construction requirements that when you construct a standard hydrogen electrode, the wire you use is platinum, and even though the electrode is also platinum. Then we have 1.00 mole per dm cube concentration of hydrogen ions in the electrolyte, and then the conditions you already know that 101 kilopascal, which is 1 atmosphere, hydrogen gas is pumped over the platinum electrode. There are three kinds of half cells. One half cell is where a metal is in equilibrium with its ion. Another is when a non-metal is in equilibrium with its ion. And the third is where two ions have the same element, but the same element is in two different oxidation states, and there's an equilibrium between them. So in order to construct the first kind of cell, the electrode is made up of that metal, the electrolyte has the metal ion, and the wire itself is made up of the metal. When we talk about the non-metal in its ion, the problem is that we can't make an electrode of the non-metal. For example, chlorine can't give you an electrode, bromine can't give you an electrode, simply like that. So what actually happens is that in this case, you treat it like standard hydrogen electrode. You have the platinum wire, you have the platinum electrode, and the non-metal gas generally, or fumes of the non-metal, are actually provided on the surface of the platinum electrode, and the ion is obviously 1 mole per dm cube. The third, when we have an equilibrium between two ions, again we have a platinum electrode and platinum wire, and both ions have a 1 mole per dm cube concentration. Then we talk about how standard reduction potential helps us determining whether something will oxidize or not. So standard reduction potential can be positive value, it can be a negative value, or it can be a value of 0.00 volt, which is the considered value for hydrogen electrode, standard hydrogen electrode. If something has a positive reduction value, it means it's a very good oxidizing agent. It will readily gain electrons. It will make sure that reduction half equation proceeds in the forward direction, which means reduction actually happens, and these kind of species normally gain electrons very readily. Since they are gaining electrons, they try to become the positive terminal. If something has a negative reduction potential value, they are very good reducing agents. Their half equation never proceeds forward, rather it moves reverse. They lose electrons readily, and they generally become the negative terminal, losing electrons. For example, zinc half cell, sodium half cell, lithium half cell, they have a highly negative reduction potential value. Then we have equation 6 where we can see E cell is equal to the difference between the reduction half cell and oxidation half cell, or you can basically say E cathode minus E anode. E cathode is the half cell which has the more positive reduction potential value, and this is the equation which moves forward, which tends to go forward in the actual reduction side. The anode half cell is basically the half cell which has less positive value, which is more negative, a smaller value, and it generally reverses because it can't proceed in the forward direction, so it is reversed. The feasibility of any kind of cell is determined by the fact that each cell should be positive value. And we also have to understand that if the ions for a forward reaction are not available, it reverses inevitably. Now, allow me to explain the second point because we need to understand what's happening. I want you to look at these two equations, equation A, equation B. In equation A, X ions gain electrons and become X metal, or X whatever, X let's suppose atom. And in equation B, Y ions gain 2 electrons and become Y. The reduction potential value for both are given. Now imagine scenario A where you have X ions and Y. Since you already have X ions available in equation A can be used the way it is. You don't have to reverse equation A. But you don't have Y available, but your scenario says that you have to use Y ions. Sorry, you have to use Y. If you look at equation B, Y is a product. So you have to reverse equation B. So equation B is reversed because Y should be used as a reactant. When you reverse equation B, the reduction potential value for equation B should also be reversed, and it can't be called reduction value anymore because you are reversing equation B, and now it will start to look like oxidation equation. It won't look like reduction. You are reversing equation B. So what actually happens is equation B is reversed, equation A remains the same, and this is your net equation where X ions react with Y and give you Y ions and X. Equation B was reversed, equation A is exactly the same way. Since equation A is exactly the same way, I'm using the potential value which is 1. But equation B was reversed, so I am reversing the value for equation B potential which is minus 0.8. So the final answer becomes 1 minus 0.8, so 0.2 volt. This is a positive value, which means that if X ions and Y react, so the reaction will happen. Now imagine scenario B, where Y ions are reacting with X. If Y ions are reacting with X, equation B has to be the same way. It does not have to be reversed because in equation B, Y ions are already there. But we don't have X, so equation A has to be reversed so that X can be made a reactant. And in order to make X the reactant rather than the X ion, so A should be reversed. When equation A is reversed and equation B is the same way, we will also understand how the net equation is written. That X is reacting with Y ions to give you the two products. I repeat, equation A was reversed because X should be the reactant in our case, and we have to reverse equation A. Now if we reverse equation A, the potential value which is 1 volt is also made into negative value. So 0.8 minus 1 which is minus 0.2, so scenario B is not a feasible case. Now you need to understand how this equilibrium works. If iron 3 ion concentration decreases, the equilibrium will start to move towards the left. And when it moves towards the left, the reduction potential value decreases. If the concentration of iron 3 ions increases, the equilibrium will move towards the right, which means the reduction potential value increases. Another scenario is if I'm meddling with the concentration of iron 2 ions. If iron 2 ion concentration decreases, the equilibrium again moves towards the right, which means the reduction cell value increases, and obviously it will also affect the net cell potential value. If the concentration of iron 2 ions increases, it will push the equilibrium towards the left, which means the reduction potential value decreases, and this will obviously affect the E cell value. Then we have a Nernst equation, which is equation 7, which is used when the cell potential has to be calculated, but the concentrations are not 1.00 mole per dm³. So you put the concentration of the oxidized form divided by the concentration of the reduced form, and then you take the log and then you put it in the net equation. Last equation from this chapter is basically calculating the Gibbs free energy Using the equation, Gibbs free energy is equals to minus like Faraday times E cell times N. N means the number of electrons gained or lost. So it means number of electrons involved in the half equation. This is all about the electrochemistry. Obviously, this is just a review, and for actual detailed studying of this chapter, I would recommend watching all the videos of this chapter. Stay tuned, guys. Thanks.